Good day, everyone. I am Noel Dumalag from Bisabit 2A.
Moving on to the Module 3, Lesson 2, Tangential and Normal Components of Acceleration. So, a little bit introductions. In mathematics, given a vector at a point on a curve, that vector can be decomposed uniquely as a sum of two vectors. One tangent to the curve called a tangential component of the vector, and together one perpendicular to the curve called the normal components of the vector. So what is that components? Two components are tangential acceleration and normal accelerations. When we say tangential acceleration, it allows us to know how much of the orthogonal acts in the direction of motions. When we say orthogonal, it intersecting or lying at right angle. So it is a perpendicular lines. Normal acceleration, it is how much of acceleration is orthogonal to the tangential accelerations. When a particle moves along a curved path, it is sometimes convenient to describe its motion using coordinates other than Cartesian. When the path of motion is known, normal symbolized with small letter n and tangentials symbolized by t or small letter t. Coordinates are often used. In the nt coordinate system, the origin is located to the particle, or the origin moves with the particle. The t-axis is tangent to the path or curve at the instant considered positive in the direction of the particle's motion. The n-axis is perpendicular to the t-axis with a positive direction toward the center of curvature of the curve. So when we say curvature, it is a degree to which something is curved. Okay. The positive n and t directions are defined by the unit vector or u sub n and u sub t respectively. The center of curvature, or O, always lies on the concave side of the curve. The radius of curvature, P, is defined as the perpendicular distance from the curve to the center curvature at that point. The position of the particle at any instant is defined by the distance S along the curve from a fixed reference point. Okay. In the velocity in the anti-coordinate system, the velocity vector is always tangent to the path of the motions in t directions. So when we see the velocity the directions, it always lies on the t direction or the horizontal directions. The magnitude is determined by taking the time derivative of the path function s of t. V is equals to the v u sub t, where v is equal to the s is equal to d s over dt. Here, v defines the magnitude of the velocity, speed, and u sub t defines the direction of the velocity vector. So here, in acceleration in the anti-coordinate system, acceleration is time rate of change of velocity, where a is equal to dv all over dt is equal to d quantity of v u sub t all over dt is equal to v sub u v u sub t plus v um, u sub t. Here, the prime v represents the change in the magnitude of velocity, and prime u sub t represent the rate of change in the direction of u sub v. After mathematical manipulation, the acceleration vector can be expressed as acceleration, or a, is equal to the prime v u sub t plus the quantity of v squared all over p times u sub n is equal to the a sub t u sub t plus a sub n u sub n. So the distance cd represents the difference in velocity between v sub u and v sub a due only to the difference in the direction of these velocities, for otherwise points c and d would coincide. Thus, we have resolved the total change in velocity into the two components, one of which is d sub d and e is due to change in the magnitude of the velocities, and the other cd to the change in direction of the velocities. Denoting cd by change in velocity sub n and de change by v sub t gives change of v is equal to change of vn yielded to change and v sub t. Dividing this relation by the elapsed time change in t during which change in v was measured gives change in v all over change in t is equal to change in v sub n all over change in t yielded to change of v sub t all over change in t. Each new vector in equation b represents the average acceleration direction of each change in velocity in the limits as the change of t approaches zero. These equations becomes dv all over dt is equals to dv sub n all over dt, yielded to dv sub t all over dt, or accelerations or represented by letter a is equals to a sub n yielded to a sub t, in which a is instantaneous acceleration at point a and a sub n and a sub t are its components. This is shown in figure 11 to 10. The magnitude of the resultant acceleration is given by a is equal to square root of a sub n square plus a sub n square, and its inclinations with the normal by the tangent a is equals to a sub t all over a sub n. Note that carefully that a sub n or a sub t is equals to dv sub t all over dt represents only the rate of change in magnitude of velocity, and that it will be zero if the speed is constant. Okay. Let us now consider the geometrical significance of permitting change of t to approach zero as limit in figure 11.8. Point B approaches to within a different distance ds of point A. Point A angle change in theta becomes d theta. The radius of curvature of B also becomes r. In figure 11.9, as change in theta yielded to zero, angle OCD become approaches 90 degree, and hence in the limit direction of CD is normal to the curve at 80. Likewise, the direction of DE becomes tangent to the curve at A. This accounts for the names, normal, and tangential components of acceleration. Hence, A sub n or a dvn all over dt is equal to v a d theta all over dt is equal to va over t ds dt is equal to va over r. Va is equal to va squared all over r. If we denote the velocity at any point by v, the normal acceleration is a sub n is equal to v squared all over r, while the tangential acceleration is a sub 1 is equal to dv over dt. Note that figure 11.5 express the normal component of acceleration as varying only with v and r. So that if the path is straight, will be indicated and a sub n will be 0 for curve path. A sub n will be 0 only if v is 0. Take note of that. Figure 11.11 shows how the total acceleration A may be resolved into either rectangular components. Either set of components may be derived from the other by projecting one set upon the other. Go. And that's all. The end of my presentation. Any questions? So if there is a question, you ask me. Thank you.